You can hear me at the back? Yeah? Okay, great. So I'm going to give you guys 2 lectures. The first one is going to be explaining some of the background of how we observe radio pulsars and fast radio bursts. And tomorrow I'm going to really focus just on fast radio bursts, what they might be, what we've observed so far. But today's first lecture is really about giving some foundation to understand how we detect these things and what some of the considerations are when we look at the data and what we can learn from the data as well, what physical insights we can draw from the data. And I'm going to give you, at the end of the lecture, I'm also going to give you guys a link to a small practical project. I have some data on a fast radio burst that you guys can download and analyze and do some nice stuff with, and maybe get a feeling for that. Because my impression is most of you are not working on observational data. Is that correct? No. Yes, that's no. Yes, you aren't. Or yeah. Yeah. Okay. All right. Yeah, and tomorrow, like I said, I'm going to explain more some of the interesting observations we've made. And just in case you were curious, this title slide is showing from a recent result where we localized a fast radio burst to very, very high precision on the sky. I'll explain how that was done tomorrow, but that's what this comes from in this kind of sci-fi looking diagram. Well, the pulse is real data, but the rest is obviously not. So I'll just introduce myself for 2 minutes. My name is Jason, as you've already heard. I'm Dutch-Canadian. I live in the Netherlands, and I work at the University of Amsterdam, the Anton Pannekoek Institute, which is in Amsterdam. But I also work at the Dutch Institute for Radio Astronomy, so it's kind of our Puccino, I guess you could call it. And Astron, we have two major radio telescopes. We have the Westerbork telescope array, which is an interferometer, and also the LOFAR telescope, which is a different type of interferometer. And just to give you a feeling for the kind of stuff I do, so this is an image of the center of LOFAR. LOFAR is this distributed network of radio antennas. It's distributed over the Netherlands, but also over Europe. This is an image of the center of the array. The array is composed of tens of thousands of antennas, which are combined through digital and analog electronics. And what you're seeing in this kind of circular island, which is at the center of the telescope, are some of these antenna elements. Those black boxes there, those are essentially plastic and styrofoam boxes that contain multiple antennas that can receive radio waves between wavelengths of about 110 to 190 megahertz, so kind of radio waves that are about this long in wavelength or so. And then you can maybe just barely see it, but in between the black areas, there are a different type of antenna that's sensitive to even lower radio frequencies. And one of the main things we do with this is we look for radio pulsars. I think all of you have a very solid background in neutron stars and are familiar with neutron star magnetospheres and whatnot, but maybe a little bit less so with radio pulsars specifically. And what we're doing with this telescope, for instance, is we're searching the sky to try and find new interesting pulsars. And one of the interesting pulsars that I could highlight to give you an impression for why we do this is this one that we discovered last year. What's shown here on the right is the computing infrastructure that went into discovering this source. So to give you an impression for the computational challenge in radio astronomy, it's quite large. Typically we have access to supercomputers and GPU-based algorithms to try and process the data, because radio astronomy is an area of astronomy in which the data rates and data complexity is extremely high. And on the left-hand side, this is a detection of a new neutron star. This is a radio pulsar that spins at a rate of 707 hertz, so it's spinning 707 times per second. This makes it actually the fastest spinning neutron star in the galactic field that we know of. And so you guys become familiar with this type of graph. The way we visualize the data is not by making an image of the neutron star, because the neutron star is just a point. It's just a point source of radio waves. But of course, we look at the pulsations from it, right? And what's shown on the left-hand side there, that graph, is the pulse profile, so the sweeping radio beam that's coming from the pulsar. It's shown twice for clarity, and it's shown as a function of time and rotational phase. So the x-axis is showing you different phases of the neutron star as it's rotating around, and then at a certain point that lighthouse-like beam is pointing towards you, and as a function of time, in this case, it's fairly constant. What we've done here is we've actually stacked all of the individual rotations on top of each other to build an average pulse profile at the top there, and that's how we detect the source. This is how we determine its rotational rate. And again, what's interesting about this source is that it's now the fastest spinning neutron star in the galactic field. And what we're trying to do is find sources that are spinning even faster, because one of the interesting things you can do with such a fast rotating neutron star is you can limit its radius You can balance the gravitational and centrifugal forces, and you can figure out, what is the maximum radius of that neutron star. And that's one of the main reasons we're looking for neutron stars with LOFAR. And what's interesting is that a lot of these sources, they have what we call very steep radio spectra. That means they become extremely bright at low frequencies for whatever reason, maybe related to the pulsar emission mechanism itself. And finding them with LOFAR is an interesting way of approaching this problem. So I'll skim through these slides pretty quickly because I think this is well known to the vast majority of you. But if it isn't, then this is just very quick. Obviously, radio pulsars and neutron stars in general were discovered about 50 years ago by Jocelyn Bell and Tony Hewish using a telescope actually that was not that different from LOFAR. What Jocelyn is standing in front of is really just an array of dipole antennas, radio receivers that are sensitive to the same wavelength radio waves as LOFAR is sensitive to. In those days, the amount of available computing power was insufficient to discover a source like the one that I just showed you. This requires much higher data rates and requires much higher frequency resolution as well. In fact, back in the day, I think you probably have heard before, these original detections were made using a chart recorder instead of using computer infrastructure that can actually record the data at high time resolution. So there you can see the detection of the first pulsar. Now, what's important about radio pulsars and fast radio bursts in general is they give us access to these extreme neutron stars that we would not otherwise have. They're a beacon, right? They're allowing us to study the physics of the neutron star and its environment because we have this really handy tool, this radio flash. As I'll show you in a few slides, it's energetically unimportant, but it allows us to detect neutron stars that would be otherwise invisible to us. And it's also important to realize that, despite the fact that we have a few thousand radio pulsars in our galaxy, this is a tiny fraction of the total number of neutron stars that are in the Milky Way. So we have this lighthouse-like beam, as I'm sure you're well aware. We think it's produced above the north and south magnetic poles of the neutron star. For slow pulsars, at least, we think there's a dipolar magnetic field geometry. We can talk about radio pulsations, but as I'm sure most of you are aware, we can also detect X-ray pulsations and gamma ray pulsations from some of these neutron stars as well. And the thinking is that these come from different parts of the neutron star magnetosphere. So whereas the radio comes, for instance, from above the neutron star polar caps, perhaps the gamma rays are coming from closer to the light cylinder. Now, if we measure quantities like the spin period of a neutron star and its spin period derivative, we can start looking at the rotational energy budget. This is probably also something that you're familiar with because you've heard about magnetars before, and you've heard about the fact that magnetars are releasing more energy than we can explain with this rotational energy budget. And the idea is that most of the energy that's being released by the neutron star, or pulsar in this case, is in a paraplasma wind. It's only a very tiny fraction, almost inconceivably small fraction, that's released in the radio. But again, this gives us a beacon where we can measure fundamental properties of a neutron star. So when we talk about the properties of a neutron star, like its radius, its mass, and its magnetic field, or its spin rate, a lot of these numbers, especially the most precise numbers that we have, come from using radio pulsars and using the technique of pulsar timing. If we have enough time in the lecture, I have a little bit of an addendum, which is about pulsar timing explicitly. I'd like to explain to you guys a little bit how pulsar timing works. It's one of the most beautiful techniques in astronomy, and it provides us a way to get access to these fundamental neutron star parameters in a very precise way. So to understand fast radio bursts in the context of pulsars as well, I'll also remind you of something that you may be familiar of, which is called the PP dot diagram. So when we detect radio pulsars, we can always detect their period, or almost always detect their period, and we can also typically measure the rate at which that period is changing, the period derivative. So we can plot these sources in a diagram that we call the PP dot diagram, and we can see different populations of radio pulsars that have different evolutionary histories and different physical origins, let's say. So you guys have already heard about magnetars. These are the sources that in some cases are actually detected as radio pulsars now, although intermittent radio pulsars in most cases. These are sources that have incredibly long periods compared to most pulsars, but also very, very high spin-down rates. That places them in a region of the diagram where we can infer that they have high magnetic fields. I'll show you guys some equations in a second. We can see a population of young pulsars, conified by the Crab pulsar and the Vela pulsar, sources that are maybe only a few thousand years old at most. A bulk of the population called normal pulsars, double neutron star systems, which have led to incredible tests of general relativity and the Nobel Prize therefore from the Hulse-Taylor system, and also millisecond pulsars. And just so you guys have some of the background for later discussions, for instance, how do we form these very rapidly rotating millisecond pulsars? Well, we do this through a mechanism that we call pulsar recycling. And the idea here is that you start with a system in which you have a binary stellar system, some kind of massive companion and a somewhat less massive companion. Obviously, that massive star will evolve more rapidly than the lower mass companion star. It will undergo a supernova, and if the system remains bound, if it remains a bound binary system, then you can end up with a radio pulsar that would be fairly young with a binary companion. But as that system evolves over many, many years, the pulsar will eventually die after about 10 million years or so. The companion will evolve as well, and it can, in its evolution, bloat and fill its Roche lobe. It can transfer mass through the Roche lobe, creating an accretion disk, and then transfer both angular momentum and matter onto the neutron star. So we call this recycling because you start with a neutron star that is spinning quite slowly, probably not detectable as a radio pulsar anymore, and then you go from this part of the diagram where we call pulsars as pulsars in the graveyard below some threshold at which they can no longer produce radio pulsations, and then through this mechanism of both mass and angular momentum accretion can be recycled to spin at much higher rates. So, and some of the beautiful things that we can get from pulsar timing are by measuring this period and period derivative, we can get not only the energy budget as I was showing you before, we can get an idea for the age of the source. So based on simple assumptions about whether the source has a dipolar magnetic field, the geometry of that magnetic field, and the initial spin rate, we can calculate what we call a characteristic age, shown by tau there. It's simply the period over 2 times the period derivative. And we can measure a surface magnetic field strength. So again, radio pulsars give us access to neutron star properties that would be difficult to ascertain by other means. Although, of course, from X-rays there are other ways of getting at neutron star properties as well. So most of that you probably know already, or at least it's a refresher. Let's talk a little bit more specifically about radio telescopes and some of the concerns for observing pulsars and fast radio bursts. So there are many pulsar observatories in the world. As I'll show you, we have both single dish radio telescopes and we have interferometric arrays like LOFAR or the giant meter wave radio telescope in India. So many radio telescopes in the world that are observing pulsars. They're typically enormous instruments because one thing you should appreciate is that pulsars are incredibly weak. We need these large instruments because the vast majority of pulsars are barely detectable even with the largest radio telescopes in the world. I'll also mention, since I know there are a lot of people working on theory in the audience and maybe think we don't have access to these types of instruments, most of these instruments are actually open access. So if you have a scientific idea, you have a theory that you want to test, you can apply for observations with basically any of the telescopes that are listed here. You can write a scientific case, you can submit a proposal, and it will be judged on its scientific and technical merit, and you will receive data if it's judged well. So let's talk a little bit about telescopes that are composed of multiple dishes, because this will be relevant for when we talk about localizing fast radio bursts. So many of the telescopes that have observed pulsars in the past have actually been single dish elements. And this is a telescope in which you have just a single parabolic reflector, or it could be spherical in some cases, with a receiver. And the field of view of such a telescope is really basically just the diffraction pattern that you get from this kind of aperture. So the field of view, the width of sky that you're observing at any time is basically just proportional to the observing wavelength over the size of the dish. So D is just here, simple diffraction formula. And this is fine for observing pulsars because pulsars are point sources. There's kind of not so much point trying to resolve them, make a beautiful image of a pulsar. But this is quite limiting. In fact, if you take a telescope that's as large as Arecibo, it's 300 meters across. It's one of the largest telescopes on Earth, shown there. The field of view that you get at a typical observing wavelength of about 21 centimeters, so radio waves that are about this long or so, if you divide this by 305 meters, the field of view that you have is comparable to about 3 arc minutes. So it's not a very large field of view, but more importantly, if you want to resolve the position of sources on the sky, or if you want to make an image that has high angular resolution, then you have to find some other trick. And the issue is that it's not possible to build a dish that's much larger than this. Yeah?
So, localizing the measurements?
Yeah, that's right.
How do you deal with man-made radio systems? I don't imagine that.
Yeah, so I wasn't going to talk a lot about man-made radio interference, but I can talk about that for a minute right now. One of the big challenges in observing is not just the large data rate and also the quest for high angular resolution. It's the fact that everyone has a cell phone or spark plugs from cars or lightning, digital audio broadcast as well. When you observe, for instance, a pulsar, typically what we're recording, as I'll show you guys in a bit, is kind of a matrix of brightness as a function of frequency and time. So you can imagine having a data cube where you have the brightness of the signal for each frequency channel and time. So you can kind of divide this data cube up into chunks where each chunk has is looking at the brightness of the source for a small amount of time. And that's kind of typically on the order of, say microseconds, maybe 100 microseconds or something like that. And each one of the frequency channels is maybe only like 0.1 megahertz wide or so. So you're dividing this observing bandwidth into small chunks and whatnot. And you're right that the signals that come from man-made interference are much, much stronger than astronomical signals. But fortunately, for the most part, those signals are either constrained in frequency or in time. So if you have some radio station, for instance, typically it's emitting at a very specific frequency. Maybe if you have a radio station, it would be, say, 92 megahertz or something like that. And then what you can do is you can excise those specific frequency channels. Oh, sorry, I should have done that in this direction, actually. Or you can have, you can excise specific frequency channels. Or if you're having problems with, for instance, a radar system, like Arecibo has a military radar that's nearby, and this is sweeping around. And once every 12 seconds or so, there's a beam from this radar that's looking for drug dealers trying to get to Puerto Rico. You can excise the data every 12 seconds because it's confined in time for a short amount of time. So you basically blank out this time. And what you end up with is then a data cube in which you've excised things in time and frequency. And if you're lucky, 90% of the data is still left. Yeah? Right, good question. But I was talking about angular resolution as well. And so the question becomes, how do we get around this? If we want to make images that have high angular resolution, or if we want to localize sources on the sky with very high precision, how do we get beyond the fact that even the largest dish that we have, its angular resolution is only a few arc minutes, and that's really insufficient. What you want is arc second resolution or sub-arc second resolution. And the way you get around this is the same way that this has been done in many areas of astronomy and physics, is you use an interferometer. So you start coherently combining the signals from multiple elements. And what's nice about that is instead of just having a single dish, if you have two dishes that are separated by some large distance from each other, then what matters is the distance between these dishes, not just their apertures. So you can start achieving a resolution which is comparable to d prime in this case. So you can start getting resolutions that are sub-arc second. In fact, in radio astronomy, we can achieve the highest angular resolutions of any area of astronomy because we can place radio dishes over the entire Earth and we can use them phase coherently. We can add their signals in a phase coherent way. And we can even do this with dishes in space, like the Radio Astron telescope that's operated from Russia. So what we do in that case is we combine the signals from multiple telescopes using a device called a correlator. We basically multiply the voltage streams between two telescopes. That gives us information about both the brightness of a source and the phase relationship between the source of those two telescopes. And we can track this with a telescope like Westerbork. But this is a nice illustration of why we build telescopes the way we do, because Westerbork, for instance, is built in a single line. So the Westerbork array is built in an east-west array. We have a bunch of dishes. They're all in an east-west array. And they span a large distance. They span about 3 kilometers or so. And this gives very high angular resolution, but of course it only gives high angular resolution in one direction, right? Because the telescope is extended in one direction, but in the other direction it is not extended. So to do this properly, you actually need to either build a telescope that has some kind of two-dimensional extent on the Earth, or you need to use the Earth to help you fill in the image. So let me just skip over and show you this image. This is an image of the famous Cas-A supernova remnant. It's one of the brightest radio sources in the sky. I think it's in the top few brightest radio sources in the sky. And this is an image that was made with the Westerbork telescope. And what this movie is trying to emphasize is it's stepping through 1 hour of data, 2 hours of data, a few hours of data, eventually 12 hours of data. What happens as the telescope is observing over the course of 12 hours is, of course, that array is rotating with respect to the sky. And what this is doing is essentially filling in that angular resolution in different angles on the sky. So it allows you to image. At the center there, you can see the supernova remnant. It's a beautiful image of it. But you see also all of these rings. And these are diffraction rings, which has to do with the spacing between the telescopes. So radio astronomers also need to, when we make an image like this, we need to deconvolve that image. We need to remove these artifacts, which have to do with the discrete sampling of the radio brightness of the sky because of the distribution of the telescope. But if you do this, and techniques have been developed over the last 40, 50 years to do this with very high precision, you can make very high resolution, very accurate, very robust images of the sky. So what that means is a radio telescope can both detect radio pulses from a pulsar from a fast radio burst, but it can also make images. And the way this is typically done is that if you make an image of the sky, as shown on the left here, this is data from LOFAR from a number of years ago. This is just an area of the galaxy where there's not too much going on. Most of the sources are just simple point sources there. But one of them happens to be pulsar B0329 plus 54, and that's the brightest pulsar in the northern sky. It doesn't look that obvious, different from all of the other sources, which are predominantly extragalactic sources. But if you turn up the time resolution, if you record the data at an adequate time resolution that you can actually resolve pulses, then you see a radio pulsar signal. Now, the issue that we have in radio astronomy right now is making an image like this requires us to use very low time resolution. And that's because we're recording individual cross correlations between different elements in the array, and that means you're storing a lot of data. You need to know the phase relationship and the brightness for all of these different elements in the array. So for each 2 pairs of elements in the array, you're storing something that's called a visibility. And you're taking all of these different combinations, and then you massage all of those data into an image eventually. You use actually a 2-dimensional Fourier transform to relate the distribution of the telescope on the ground to the sky brightness. And when you do this, what you need to do is you need to create an image maybe only once every second. Otherwise, the data rate would be much, much too large. Now, if you, instead of making an image, if you trade in all of that angular resolution or all of that information about how bright the sky is in different directions, if you, instead of cross-multiplying all of these different combinations of telescopes, if you just add them all together, then you can afford to record the data at much higher time resolution. And that means that for pulsar observations, we typically lose all information about where the source is in the field, but we can detect each individual pulse. So this observation, for instance, is showing you individual pulses from this pulsar. They've been stacked on top of each other to produce that average profile. And I'm telling you this, it might seem kind of detailed, but I'm telling you this because this is also the way we detect fast radio bursts. And that means that when we detect a fast radio burst, typically, we don't have some nice image of the sky where we can localize the source on the sky and say, oh, this must be the galaxy it's coming from. What we have is a nice detection of a pulse signal, and it's somewhere within the field of view of the telescope. We don't know where it is, and this has been incredibly limiting in terms of being able to make progress in understanding what this phenomena is. But as I'm going to explain in more detail tomorrow, we've actually localized one fast radio burst source, and that has provided a wealth of information on the physical origin. So yes, I just wanted to establish that point. Now, I've just told you actually that in radio astronomy, we typically either make an image where the time resolution is very low, or we make a pulsar-like observation where the time resolution is very high and we can see individual pulses. Actually, we're starting to scratch the surface of doing something that gives you everything at once. And this is a nice illustration from Casey Law, who works at UC Berkeley. What he was able to do is record data at a very, very high rate and look towards the Crab pulsar. And what you see is once per loop of this film, you can see a giant pulse from the Crab pulsar. So the Crab pulsar is very young. I think you guys know that it's about 1,000 years old. It produces these giant pulses, which are the brightest radio pulses that we have detected to date, besides the fast radio bursts, which are more luminous. And what you can see is whenever that pulse comes, you can actually image where it's coming from on the sky. But if you're looking carefully, you'll notice that whenever it flashes, it's flashing in many, many different places. And I guess I could ask the question, does anyone have any idea why it's flashing in many different directions at once? Because obviously there's just one source. It should be coming from one direction on the sky. Why do we get this complicated pattern every time it's flashing? It's kind of a tricky question, but maybe, can someone guess? Yeah? Oh, the axes are right ascension and declination. So this is just position on the sky. So you'd expect, if it's coming from a single source, it should just be flashing at one point of the sky, right?
What was the diagram of the receiver?
Sorry?
What's the diagram of the receiver?
Yeah, it's related to that, yeah.
Yes, if you've got an array, then you have multiple solutions, like your diagram has multiple maxima in different directions, and you don't know which of these maxima the signal is coming from.
Yeah, so if you have a regularly spaced array, that is the answer, yeah. Basically, that's the answer. If you have a regular array, is it okay to use this? So imagine you have a two-dimensional telescope array where the telescopes are distributed, say, in a grid on the ground. Then indeed, when you look at some source on the sky, each one of these is pointing towards that source. You can move that source on the sky and still get the same phase relationship between these telescopes, right? So what this means essentially is that the sensitivity pattern of the telescope is a diffraction pattern. And this is a very simple example using LOFAR. This is just a data set that I took where these two individual stations of LOFAR antennas, they're both pointing up at the zenith, so they're both pointing straight up. So you can see those two hexagonal black areas as basically just two telescopes that are looking straight up. You don't move the telescope at all. You don't try and track the source in the sky. You just let a source pass over the telescope. And when you combine those two telescopes together, you basically get a diffraction pattern. It's like a young double-slit experiment, right? So the sensitivity pattern of the individual telescopes is shown in blue. You get some field of view on the sky. But when you combine the two together, you get this yellow kind of fan beam pattern. So as the pulsar passes over, you can see in the data that's shown at the top and that's shown on the right here, it becomes detected, it disappears, it becomes detected again, and it disappears again. And that's the same thing that's happening here, so it was a good answer. Essentially what's happening here is, because for a short instant of time you get this flash, we can't actually localize the source very precisely in the sky. And this means, and this will become relevant when I talk about localization of fast radio bursts, that you actually want to build telescopes that have much more complicated kind of pseudo-random distributions on the ground, because you want to downweight these what we call side lobes. So you want to downweight a field of view of the telescope that kind of looks like this. You want to construct the telescope so that its sensitivity pattern has very low response in most directions and a very strong response in a very specific, well-defined direction. So this is all, this is all just Fourier transforms, right? The distribution of the telescope on the ground basically dictates what its sensitivity pattern is on the sky, and you can build the telescope such that you can make a cleaner field of view on the sky and better localized sources. Yeah.
So this issue would exist for any kind of telescope.
Yeah. Yeah, you should really just think of it as some aperture, and if you take the Fourier transform of that distribution, it will tell you what the response of the telescope is on the sky. But then if you're smart about it, you can build a telescope that will give you a more focused response, let's say. Okay. All right, and one last thing about imaging and pulsars before we continue. We're also starting to get into the regime, actually, where we're finding pulsars that are so slow that we're finding them in images anyway. And I couldn't help but showing this one recent discovery. This is something that we found just a few months ago, and I think it's noteworthy enough to mention in the lecture. So to told you already, we've been doing this large survey with LOFAR looking for very fast spinning neutron stars to try and limit the radius of neutron stars. In the process of that, we came across something really unexpected as well. We found a radio pulsar that's spinning at 23.5 seconds. So the average radio pulsar spins maybe once a second or so. That's kind of a typical pulsar speed. The Crab pulsar that I was just showing you spins about 30 times a second, so much, much faster. The very fast spinning pulsar that I showed you at the beginning is spinning hundreds of times a second. But this one is spinning only once every 23.5 seconds. So this is by far the slowest rotating neutron star we've ever seen radio pulsations from. This diagram, which is similar to the one that I showed you at the beginning, is just showing you the pulse strength as a function of time. You can see that the pulse is incredibly, incredibly narrow. So there's just a very small fraction of the time. You could basically, you look at your watch for half a minute or so, and then just for a few milliseconds, there's a little burst of radio waves, and then it goes away again. But since we can make images once a second or so, this actually shows up in our LOFAR imaging surveys as well. So you can detect this at high time resolution using this mode in which you add all the telescopes together, but you can also make an image of the sky at sufficient time resolution that you can actually localize the source on the sky as well. So this image in the bottom left-hand corner here is just showing you how that same pulsar looks like in a radio image. And what this means actually is now we've been able to extend the PP dot diagram for pulsars, both in the fastest spinning pulsar and slowest spinning pulsar. And what's interesting about this new source is, if you guys have heard in some of the other lectures about the pulsar death line beyond which pulsars become inactive, this source is actually reasonably well into the pulsar graveyard. Okay, so let's talk about some more of the observing challenges when it comes to detecting pulsars and fast radio bursts. But maybe before I jump to that, I should ask, are there any questions about what I've... Let's talk about propagation effects. And by propagation effects, I mean ways in which the electromagnetic signal is disturbed as it's traveling from the source towards us. And this is absolutely critical for understanding the fast radio burst phenomena. It's one of the main ways in which we can, well, it's the only way, essentially, in which we can determine the distance to fast radio bursts in general. And it teaches us a lot about what they might be. So the propagation effects that I'm going to discuss are dispersion, scattering, scintillation, Faraday rotation, and we could also talk about ionospheric phase delays. The important point is, if we look at this simple equation here, S of t is telling you the intrinsic signal of a source from the emitter. So that's just, it could be a pulsar, it could be a fast radio burst, it could be some other source. That signal is modulated in time. It's just the brightness of the source as a function of time. And then that source, that signal is disturbed in various ways before it reaches us. And what we actually record is this I of t. That's what we actually record at a radio telescope. And the ways in which it is modulated are by these various effects which disturb the radio waves. These effects are what we call strongly chromatic. That means that the strength of the effect varies very strongly with observing frequency. And that means that actually most of these effects become extremely strong towards low radio frequencies, but they're also measurable at reasonably high radio frequencies. And they make it difficult to detect pulsars. They make it difficult to detect fast radio bursts, but at the same time, they provide a lot of useful information. So the first one, which you guys will come across when you're doing the simple practicum, when you're looking at the data that I've put online, is the effect of dispersion. Now, dispersion has to do with the frequency-dependent light travel time of the wave. So as the signal is propagating through the interstellar medium or through the intergalactic medium, it's encountering free electrons. And these free electrons create dispersion, and that means that the signal actually arrives later at low frequencies than it does at high frequencies. And with a radio telescope, we typically observe over a large range of frequencies because otherwise we don't have enough sensitivity to detect anything at all. So we have to record a wide range of frequencies, but then we also need to correct for this effect. And so far, the graphs that I've been showing you are all corrected for this effect, but this is not how we get the data. So on the left-hand side is how the data would actually appear. If we're observing, say, from 110 to 190 megahertz radio frequencies with a telescope like LOFAR, the pulse from a pulsar will be swept. It will be swept quadratically because the delay in time is proportional to frequency squared. In this case, you can see that the signal is always arriving later at lower times. And if we correct for this effect, then we can straighten out the signal so that it arrives at the same time at all frequencies. And the way in which we make this correction is by taking these individual frequency channels and correcting for this extra time delay in each frequency channel. I'll show you a diagram in a second, but this is one of the things that I want you guys to try with the data that I'm providing. In this process, so we have, so again, just so everyone's clear, we have a source that's up here, we have an observer down here, and we have a bunch of material between us and the source, and the radio waves are passing through this material, which has some electron density. And what we're measuring here is this dispersive delay, and the degree to which this delay occurs, the magnitude of that delay. Like I said, it's frequency dependent, but it also depends on how much material the signal is passing through. So it depends on the electron density along the line of sight. So we measure this thing that's called the dispersion measure. And what the dispersion measure is essentially giving us is the integrated column density. So it has units of, has these crazy units of parsecs per cubic centimeter. It gives us the column density of free electrons along the line of sight. So we don't have any three-dimensional information, but we do have a one-dimensional line of sight through the galaxy or through the interstellar medium or through the intergalactic medium that tells us how many free electrons are along the line of sight. And this will become useful because what you can realize is we correct for this effect so that we can look at the intrinsic shape of pulses from FRBs and from pulsars. But what's nice about this is that we can also use this as a proxy for distance. So if you have a model, if you construct a model of the Milky Way, for instance, in which you model how many free electrons, the electron density at any part of the Milky Way, then you can turn this around and you can use the measured dispersive delay to calculate a distance. So what's shown here, this is from a model by Jim Cordes and Joe Lazio that's been around for a long time now. There are some more recent models. But on the left and on the right, what is being shown are iso contours, so contours of constant dispersion measures, so constant column density, both looking down on the galactic plane from above and looking across the galactic plane, so making a cut through the galactic plane. The Earth is the circle, and the galactic center is at coordinate 0, 0, so it's down towards the bottom there in the case of the left-hand diagram. And what you can see is, if you look in different directions in the Milky Way, you accumulate different amounts of free electrons, right? If you look towards the galactic center, unsurprisingly, you don't have to go very far before the dispersive delay becomes very large because you're encountering a large column density of material. To put it another way, if you're looking out of the galactic plane, instead of across the spiral arms, you're not encountering very much material, so you have to go a very long distance before you accumulate a large dispersive delay. And if you're looking within the galactic plane, then that accumulates quite rapidly. So you know the position of the source on the sky, you have this model, and you measure this dispersive delay, and with all of those things, you can come up with a proxy for the distance to the source, right? So keep that in mind because it's really important for fast radio bursts. And again, we can correct for this, and we have to correct for this when we detect pulsars. And typically the way we do this is we channelize the data. So I told you guys before when we got the question about radio interference that what we're essentially recording for fast radio bursts and pulsar data is a data cube of brightness versus frequency versus time. And then there's interference in there, as I just drew, but then there's also this astrophysical signal that is sweeping with frequency. What we need to do is we need to channelize the data. So we split the observed radio frequencies into a bunch of independent channels. And this can be done using a polyphase filter or even a very simple Fourier transform on the raw band. And you can record the data at the Nyquist limit if you want to, or you can downsample. And what we can do then is each one of those can be shifted in time, right? Because the signal is arriving here later than it is here, but that's okay because we have these discrete time samples and we can shift the signal backwards in time to line everything up so that when we correct for this, we actually get a single pulse peak when we add all of the frequencies together, right? So that's what's being shown in this diagram here. And what I'm going to give you for data to work on is also data that's channelized in time binned in, or channelized in frequency and binned in time, and you can correct for this effect and calculate the dispersion measure of that pulse. Okay, so this is how we correct for dispersion. I could go into a lot more detail about how this can be done even better than what I'm showing you here, because I suppose one of the questions you could ask is, okay, it's nice that you can correct for this by shifting all the channels, but what if the pulse is already delayed quite a bit within a single channel? Because then you're smearing out the signals still, unless you make the channels smaller and smaller, and that's true. Actually, to make a very, very precise correction for this, you need to do something called coherent de-dispersion, which doesn't channelize it. It actually uses the full phase information of the signal and coherently corrects for this delay. But it's a bit too detailed for this lecture. So that's dispersion. One of the other main things that we have to deal with is scattering. And scattering is multipath propagation. So instead of having the speed of light being frequency dependent, what we're seeing essentially is that if the signal travels through multiple paths, because it could have some kind of scattering screen, and many times this is modeled as just a very thin screen between us and the source, then because of scattering, the signal can actually arrive later because it's traveled a longer distance. This ray has traveled a longer distance than this one that's come closer to us. And what this does, as is being shown in this diagram, is you can take a pulse that is very sharp, and as you go to lower frequencies, the scattering effect becomes larger. And what happens is the pulse goes from looking like this at high frequencies to looking like this at lower frequencies. And this exponential tail comes from the fact that parts of the signal are just taking longer to get to us than other parts. Because the total time scale here is, a few milliseconds or something like that. So even a delay of a few milliseconds, which is comparable to only hundreds of kilometers or so, can produce this exponential tail.
So physically, should I think of this as the photons are losing energy as they scatter out electrons?
No, you should think of it as they are traveling a longer path. The pulsar is not emitting isotropically, but it is, there is some opening angle to the emission that's traveling towards Earth, and some of that emission is being scattered back into our line of sight. Right? So emission that would otherwise miss Earth because of scattering is being bent and is coming back and is arriving at our telescope. Right? And this is real data here. I think on the screen it doesn't really show up very well though. No, you can't really see it here. Well, you can see this exponential scattering tail, but if you could see the image with better resolution, you would see that this actually evolves across the observing band, that from the top of the observing band to the bottom, this effect becomes stronger because this actually scales as a fourth power of frequency. So this goes incredibly quickly. I'll give you a different illustration that you can probably see more easily. This is from an observation we did many years ago with LOFAR, looking at the crab pulsar, and the two curves are at two different frequencies. One was using the high band of LOFAR, so those black boxes that I was showing you, and the other curve is using these low band antennas, which are significantly lower frequency radio waves, or sensitive to lower frequency radio waves. And if you look at this gray curve here, you can see a giant pulse from the pulsar. And if you look very carefully, you can see that it has a little bit of that exponential tail that I was telling you about. Now, if you go down by a factor of 3 or 4 in frequency, then that's what that same giant pulse looks like. That pulse is actually scattered to be about 3 seconds long or so, even though intrinsically the pulse is a few nanoseconds. So you can imagine how bright a giant pulse that's a few nanoseconds long must be to still be visible when it gets smeared out by a few seconds or so. And again, this has to do with there being some kind of scatterer along the line of sight. In this case, we think that's something in the interstellar medium. It's not something in the Crab Nebula itself.
Is the difference in the peak positions due to dispersion?
That's a very good question. Aligning them, you need to know the dispersion measure incredibly precisely. Otherwise, you could have an offset, which is due to imprecise dispersion correction. But also, if the scattering becomes very strong, you don't get just a sharp rise. You actually the pulse starts bending over as well. Yeah. Because there's so few rays that come straight to us, they're basically all being scattered at a certain point. Yeah.
Why is it frequency dependent?
Why is scattering frequency dependent?
Yeah.
Sorry?
Why is it more likely for low frequency?
Sorry, I don't think I understand.
So you have a narrow beam if you have, or if you are in high frequency, right?
Yeah.
And it's a greater.
Oh yeah, so the refractive angle can be larger as you go to lower radio wavelengths. So the bending can be larger as you go to lower frequencies. So if you're at higher frequencies, you can think of it as kind of a scattering cone. If you're at very high observing frequencies, the maximum bending that you can get is quite limited. So you're only getting rays that are coming from a very narrow opening angle. But as you go to lower and lower frequencies, refraction can become stronger and stronger, and you can have a larger and larger opening angle for the scattering. Yeah. So you're essentially, what you're doing is you're probing a larger angle of emission as you go to lower frequencies. And that's interesting as well because there are inhomogeneities in the interstellar medium, and say at high observing frequencies, maybe you're probing rays that come from this kind of opening angle. And as you go to lower observing frequencies, you're probing a much larger opening angle, and you can actually use this effect to probe turbulence in the interstellar medium as well. Okay, so the next propagation effect that I want to mention is Faraday rotation, and this is also something that you're going to find in the data. I should say the data that I'm giving has basically zero problems due to scattering. You won't see any scattering effects in the data, but you will see Faraday rotation. And Faraday rotation is again due to plasma along the line of sight. It's a magnetized ionized medium, and I think everyone is familiar with that electromagnetic wave can have a polarization. You could describe this as in a circular basis, for instance, that there's a circular and that there's a right and a left polarization to the signal. And what happens if you have a magnetic field along the line of sight, the polarization hand that is propagating in the same direction of the magnetic field is actually advancing more rapidly than the one that is pointed in the opposite direction of the magnetic field. And what this creates is, if you think of a linearly polarized signal, so these are just axes of well, this is just a Cartesian axis, I guess we'll say. If there's a certain polarization angle to the signal, so the electromagnetic wave has some, can't draw this very well, but if the electromagnetic wave has some preferred direction with respect to some reference, some Cartesian grid, it has some angle at some particular frequency, you can actually have a different angle at a different frequency due to this Faraday rotation effect. So this angle is changing with frequency in a way that is proportional to the rotation measure. So this is similar to the what we have with dispersion measure as well. And it also goes quadratically with the observing frequency, or equivalently the observing wavelength. So what's shown on the left-hand side here is, are you guys familiar with Stokes parameters? Yes? A little bit? Okay, so it might be good for the practicum if you read up a little bit on what Stokes parameters are, but it's a basis for describing the polarimetric properties of an electromagnetic wave. And the Stokes I, Q, U, and V parameters can be used to describe this polarized wave. I is just the total intensity of the signal. Q and U combined give you the linear polarization. So how much of the total intensity is linearly polarized? And then V is essentially giving you the circular polarization. And what's shown here on the left-hand side is how the signal is rotating. The color scheme is showing you that the signal is going from being strong in Q to strong in U, and you can use the ratio between Q and U at any given point, at any given frequency, to calculate what the angle of the polarization is. So what you can see here is that the polarization angle is wrapping around and around. That's the difference between the red and the blue bands. I guess I could describe it that way. And as you can see, it's strongly chromatic. remember, it's scaling as quadratically with observing frequency. So at the bottom of the observing band, which is about 110 megahertz or so, you can see that it's wrapping around very, very quickly. And as you go up to somewhat higher frequencies, say 170, 180 megahertz, then it's this wrapping around is happening more and more slowly. So you can measure this in the data that I'm providing you as well. And this can give you an idea of what the magnetic field strength is. Because the rotation measure, I guess I should have given you guys these equations as well. The dispersion measure, again, is a column density. So from here to there, from us to the source of the electron density. So we're just integrating all the free electrons along the line of sight, and we're getting something that's in a column density. So parsecs per cubic centimeter is the units that we typically use. Whereas rotation measure, there's a prefactor here as well. I think it's 0.81 or something like that. What we're essentially integrating is the magnetic field weighted electron density along the line of sight. So the magnetic field parallel to the line of sight times the electron density is essentially what we're measuring when we're measuring this proportionality constant called the rotation measure. And what's nice about these two equations is if you think that the rotation measure, or the Faraday rotation, is coming from the same medium that is providing most of the dispersion measure, you can just divide these two things by each other. And then this is essentially giving you the magnetic field, right? And then the last thing that I'll mention, which is also something that you can measure in the data that I'm providing you guys with, is scintillation. And scintillation is, I mean, people typically talk about scintillation in terms of the twinkling of stars. We have delays in the signal due to scattering, diffractive, and refractive effects. And if the signal comes back on itself, and it has been delayed by a fraction of a wavelength, you can actually constructively or destructively interfere with itself. So imagine, due to diffractive and refractive effects, that the signal that we're observing has been perturbed, and here in the plane of the observer, that we're getting constructive and destructive interference of the signal with itself. The way this looks like, we can plot this as a function of time and frequency. If you take a data set as a function of time and frequency, so kind of like what we were talking about here, what you can see due to the scintillation effect are patches where the signal is particularly bright at any given time. Because at very specific times, when we're observing a source, and for very specific ranges of frequencies, you can get constructive or destructive interference of the signal with itself. So this is telling you something about the distribution of scale sizes of turbulence in the interstellar medium. And it produces effects like what I'm showing here. So that is frequency, well, it's flipped around, frequency versus time. You can see that this particular pulsar is particularly bright at certain frequencies. And you can see that there's a characteristic width in frequency for these features. In the case of this particular pulsar, these features in frequency space happen to be about 1 kilohertz wide. And that tells you something about the scales of turbulence in the interstellar medium. And one of the reasons this is interesting is because it provides, just like scattering and dispersion and Faraday rotation, it provides a way of measuring the properties of the medium between us and the source. But interestingly, this can also make sources detectable when they wouldn't otherwise be detectable. So if you spend a lot of time looking at a source, you might be lucky one day that you're looking at it when it just happens at that time to become incredibly bright because by pure coincidence, the source is scintillating up and it becomes detectable by your telescope, and most of the time is not detectable. And this is also relevant for our understanding. I'll mention this tomorrow when I go into more detail about fast radio burst observations that have been made. This could be one of the ways in which we're detecting fast radio bursts, because we're only detecting sources that get this extra boost, and then we detect the source and then we never see it again because it is highly unlikely that it will be scintillated up again. So just to summarize these main effects, because these are things that you guys are going to be looking for in the data set. Dispersion measure is a column density again. It measures the integrated column density of free electrons along the line of sight. And you can measure the dispersion measure for the bursts that I'm giving you in the data. The rotation measure is measuring the electron density weighted magnetic field along the line of sight. That's in radians per square meter. So you can essentially measure how quickly the polarization angle is changing as it's propagating through this magnetic field. Scattering. This also reflects inhomogeneity in the medium, and it's a multi-path propagation effect. And then scintillation, as I just said, is due to destructive and constructive interference due to refractive and diffractive effects. So the thing I would like to conclude on before we have the coffee break is just explaining a little bit how we do pulsar searching, because this leads into how fast radio bursts were discovered in the first place. I won't dwell on this, but as I tried to tell you guys earlier in the lecture, because of the increase in available computing power, we're actually moving more and more towards using interferometric arrays, so collections of multiple telescopes to do these types of pulsar and fast radio burst observations. And this is because it's the best of both worlds. We have a large sensitivity, but we can also localize sources on the sky very well because we have a geographically distributed telescope. But in a more general sense, how do we actually search for pulsars and fast radio bursts? So, again, what we're starting with, so you can see this kind of as like a flow diagram for what is the approach that we take with the data. And on the left-hand side is the data that we're starting with. And as we've discussed a couple times already, essentially what we have from the telescope is we have data as a function of frequency and time, and we have the brightness at each frequency and time. So it's discretized in this case. We've created frequency channels and time bins, and we have the brightness of the source for each one of those frequency channels and time bins. And we have the brightness of the source also for, basically the field of view of the telescope. So if you think of a single dish telescope, its sensitivity pattern on the sky will be kind of a diffraction pattern. So you can think of it as kind of like an airy disk. In the case of Arecibo, like I told you already, this is about three arc minutes across. We're essentially measuring the radio brightness of the sky and, unfortunately, all the man-made interference in that direction as a function of frequency and time. And then the first thing we do is RFI excision, which we discussed already. And unfortunately, most RFI radio frequency interference is confined in time and in frequency. And then what we need to do is we need to correct for this dispersive delay. So we have to deal with the fact that the signal is dispersed across a broad band. And as I said, this is an interesting way to find distances to sources, but it's really a practical challenge for finding sources in the first place, because if we look in a particular direction on the sky, we don't know a priori what dispersion measure the source might have. I mean, when we search different possible dispersion measures, so different column densities of free electrons, essentially we're looking at different depths in that particular direction. And this graph that I made is trying to illustrate that. Each line in this diagram is what you get when you collapse the data in frequency. So you've added all the frequency channels together. And you do that for a certain correction for a dispersion measure. So you've shifted these channels under a certain assumption that the dispersion measure is, say, dm0. And then you collapse everything together and you see what's in the data. Then you do that again for, say, dispersion measure 1 and dispersion measure 2. You probe the whole range of possible dispersion measures with an appropriate, sampling interval, right? So you don't lose any sensitivity to pulses. And what you can see, as a function of dispersion measure, shown on the y-axis here, and as a function of time, at a certain point, a signal becomes detectable. And that's because we're adding the whole bandwidth together. And then we have sufficient sensitivity because we're adding a large enough frequency range together that we can see this sharp pulse, which is shown in black there. But that pulse gets smeared out when we don't have the right dispersion measure. So this is one of the things that we have to, one of the parameter directions that we have to search through. Now, pulsars are obviously periodic sources, and that so it shouldn't come as any surprise to you guys that using a Fourier transform-based technique is a good way of finding them. We could talk for a whole hour about caveats to that statement, but Fourier transform is one of the main techniques that's used to find periodic pulsar signals, although now a lot of people are also doing a brute force stacked algorithm where you just probe all of the possible pulse periods, because that that preserves the full harmonic content of the signal. If you know what I'm talking about, great. If you don't, it's a detail. So we search for periodic signals, but we search for intermittent sporadic signals as well. And what this diagram is trying to emphasize here is that imagine a situation where we've corrected the data for dispersion. On the top left-hand side there, we've corrected the data for dispersion, and we've summed all of the frequency channels together. Now we can take a Fourier transform of those data, and then the Fourier transform that we get is shown on the bottom left there. So you can see multiple peaks. And why is there all of a sudden a signal? Well, I think it's important to appreciate for most pulsars, they're too weak to see their individual pulses. We actually have to stack many pulses together to be able to see anything at all. So each individual pulse is very weak in time. But if you stack enough of them together, then you'll get an obvious signal in frequency space. Now, when you stack them all together, the pulse might look like this, for instance. And the reason there are multiple peaks in Fourier space is just simply there's a lot of harmonic content in a sharp signal like this, right? Most pulsars don't have sinusoidal pulses, they have sharp pulse peaks. That means when you do a Fourier transform, you get many, many harmonics at multiples of the spin frequency. And searching these data optimally means also stacking all of those harmonics together, but that's a bit of a detail. Now imagine kind of a diametrically opposed situation in which instead of having a bunch of weak pulses that are coming with extreme regularity, imagine that you have a single very, very bright pulse, so that's shown on the top right-hand side there, but it only happens once. So you observe for a whole hour, and you just get one bright pulse. If you take a Fourier transform, obviously there's no periodicity to be had. You won't find anything. So in modern pulsar searches, we do both Fourier transforms of the data, and we do single pulse searches. Just very quickly, because I'd like to wrap up in the next 5 or 10 minutes, there are all kinds of complications to this picture. One is the fact that a lot of the most interesting pulsars are in binary systems, or in some cases even triple star systems. I don't think the projector is really doing justice to this graph, but yeah, I guess you can see it here. In the case of a pulsar like a double neutron star system, the Doppler effect is going to be changing the perceived period of the pulsar as a function of time. This will smear out the signal in a Fourier transform, right? Because the observed frequency is constantly changing. So if you were to observe, for instance, as a function of time, which is shown on the x-axis there, and a function of frequency in a power spectrum, then you can actually see this orbital modulation of two different pulsars. These are both visible at the same time because these are pulsars that are found in a globular cluster, so they're actually in the same direction on the sky. And you can see one of them has a very short orbital period and it's showing eclipses, and the other one is in a much longer orbital period. So you need to, in many cases, correct for this orbital motion when you do a periodicity search. But then the last thing that I'll emphasize is we also do these searches for these individual single pulses. And kind of one way of visualizing this is, again, what one does is we make various guesses for the dispersion measure, so how much dispersive delay there is, because we don't know that a priori. And then at any given time, well, we've collapsed all of the frequency channels together. So let's say we collapse all the frequency channels together, and then we get some pulse and whatnot. We go through what we call these time series, where all the frequencies have been squashed together. We go through with just a simple match filtering algorithm where we try different boxcar widths to search for pulses in there. We convolve the real data with these filters. And then what's shown in this diagram at the bottom there is the size of these circles in this diagram is showing you how much power there is as a function of dispersion measure and as a function of time. So you can see that at a specific dispersion measure, that's kind of a horizontal line, there are pulses that are coming. At the beginning, the source is quite sporadic. There's a few pulses, and then it becomes quite active for about 20 seconds or so. And this has become because some pulsars are highly intermittent. Some pulsars actually show one pulse maybe an hour or something like that, and they're otherwise undetectable. And this was a technique that was used in the early days of pulsar research. This is how the crab pulsar was first discovered, not through a Fourier transform, but through its giant pulses. But people have started doing this more and more in recent years because we've realized that there's a whole part of the neutron star population or pulsar population that we've been missing by not doing this type of search. And it was because of this, so just to wrap up this first lecture, it was because of this that fast radio bursts were discovered. So Duncan Lorimer, who is working at the University of West Virginia now, he was doing a project with the Parkes Radio Telescope in Australia. This is the Parkes Telescope. And they were looking for young pulsars towards the Magellanic Clouds, the small Magellanic and large Magellanic Clouds. And they were specifically doing these type of single pulse searches that I just described because the idea was, well, maybe there's some kind of crab-like pulsar in the Magellanic Clouds, and maybe the only way of detecting it will be through its giant pulses, because maybe it only emits a giant pulse once an hour or once every few hours, and there's no way that you would see some kind of regular periodic signal in the data. Now, they made a big mistake. They searched in dispersion measure space up to a dispersion measure that was just ridiculously too high. There was no way that you were going to have this much dispersive material between you and the source, but they did that anyways by mistake. So they were basically wasting computer time. But in the process of wasting computer time searching this, ostensibly uninteresting astrophysical parameter space, they came across this now famous Lorimer burst. So this is an iconic plot, which is going to be basically the start of my lecture tomorrow is describing the whole history of fast radio burst detections in science. This plot is similar to a lot of the plots that you've seen before. Frequency on the y-axis, time on the x-axis, brightness is the color scale. You can see the swept signal. That's the dispersive delay that I've told you about many times now. If you correct for that and you sum all of the frequencies together, you get that pulse there. And that's all very nice. It looks pretty much like any other pulsar pulse, except for the fact that let's look at this dispersive delay. Let's compare it to this model for the electron density distribution in the Milky Way. So we talked about how this can be used to measure a distance. If you measure the dispersive delay and you have this model and you know what direction you're looking in, well, you can combine this information to figure out how deep you're looking. And there's a big problem here. They were looking very far off the galactic plane towards the Magellanic Clouds, and the amount of dispersive delay that one can explain from the interstellar medium of our galaxy is given by that green bar. So from the top of the diagram to the bottom of the diagram, you would expect that the signal would only be swept by that extent. And instead, you see that it's swept by many, many times more, about 11 times more. So the interpretation, the scientific interpretation was, well, maybe the source is not being dispersed just by the interstellar medium of our galaxy. Maybe the intergalactic medium, which is also ionized, is also contributing to the observed dispersion of this burst. And if you make a calculation, if you take models for the electron density in the intergalactic space to try and use this dispersive delay as a proxy for distance, what you find is that this source comes from approximately 0.5 redshift, which is a lot further away than the Magellanic Clouds, and a lot further away than your typical pulsar. So observationally, at least, fast radio bursts distinguish themselves from pulsars predominantly in the fact that they produce single bright radio bursts, although I'll tell you tomorrow we found a repeating source of fast radio bursts. That's the data that you're going to work on. But they also distinguish themselves from pulsars in this dispersion measure sweep way. So if one makes a diagram, it's a little bit difficult to interpret this diagram, but it's a really nice diagram once you wrap your head around it. This is made by Jim Cordes at Cornell. If you look at the maximum galactic dispersion measure that one would expect in his model, so 1, this horizontal line of 1 tells you that anything below that line should be within our own galaxy, right? Because it could be at the edge of the galaxy and then you would reach the maximum expected dispersion measure, but if it's nearby, then it's below that line. And anything above that dashed line should in principle be extragalactic. And indeed, for instance, sources in the large and small Magellanic Clouds fall above that line. But then we also have these open circles and this green dot there. Those are the fast radio bursts. These are signals that have dispersion measures that are quite large, but also much, much larger than we can explain with our models for the interstellar medium of the Milky Way. And tomorrow we're going to talk about what they might be, because there are certainly a lot of theories about what they might be. I'm going to conclude here. I'm assuming these slides will go online, so there's actually a whole section on pulsar timing as well that we definitely don't have any time for right now, with a simple introduction to pulsar timing. Again, I mean, it's a little bit tangential to the topic of fast radio bursts, but it's really an absolutely beautiful technique for measuring neutron star properties. And to give you one example, if you don't believe me, we've recently detected a pulsar that's in a stellar triple system, and we were able to test the strong equivalence principle by essentially looking at whether the pulsar and white dwarf that are in the inner part of this hierarchical triple system are accelerated differently from each other towards the third body in the system. So we could place an upper limit on the accelerations. And this allows us to see, for instance, that the pulsar and the inner white dwarf are accelerated by a fractional amount less than a few parts in a million. So this gives you an idea how precise pulsar timing is if you can make these kinds of measurements. So I've included this in the slides as well because I think it's a nice way of illustrating how pulsar timing and radio observations can do fundamental physics. Okay, thanks for your attention.